recording?
Go ahead. Go. Okay.
Hello. Today we're talking about two important theorems of one of the first theorems you encounter in multivariable calculus, the inverse function theorem and the implicit function theorem, which kind of follow one after another, and they are also important in beginning to understand manifolds. So inverse, and I don't know how to do the symbol. Theorems. Okay, so
Okay.
yeah, okay, we're good. Okay, so we'll start with the inverse function theorem, which this one specifically is about functions from Rn to Rn. So from Rn to a space of the same dimension, because as the name suggests, we're going to explore when a function can be invertible, and for a function to be invertible, we expect it to be from the space to kind of this similar dimensional space. Now, last time I heard there was a review of what a derivative is for multivariable functions, and so last time I think we saw that the derivative is just like in the R to R case, the best linear approximation to the function at a point. So we saw that df at A is the best linear approximation, right? To f at the point A. And so what does that mean specifically? That means that near A, right? Near the point A, we can write that f of x is just f of A plus, this is the the affine part, I guess, whatever. That's df at A. This is a linear map, right? Applied to I guess x minus A, yeah. Plus an error term, also depending on x minus A, where this error term gets small even as x minus A gets small. So a limit as zero, right? This is what that means to be a very good linear approximation. And so what this suggests is that we can start to think about, we can understand local behaviors of these functions pretty well by just understanding this linear map that is the derivative. And that's what the inverse function theorem essentially is about. So let's draw a picture of sorts. I think I will. Can I slide this and move this board over here? So is it better if I?
Yeah, you can do whatever. You can rotate. We can move the table.
Yeah. I think this is even easier actually. So we're talking about this one right now. Does this start all the way? Oh, yeah. Perfect. So, okay, let's okay, yeah. What I want to say is, if f is really closely approximated by this linear map, which is its derivative, then if we want f to be invertible near a point, we can expect the condition to be that the derivative itself is invertible as a linear map, right? So, move the string out of the way. So suppose we have suppose we have Rn here, and maybe we have a domain inside of Rn, like a rectangle. Now this rectangle containing the point A, right? And we have a function. Let's first talk about what the derivative of a function would do. So what a linear map could do to this domain. The domain here is like a rectangle for visual purposes, but also kind of in general. Anyway, right. What would a linear map do to a rectangle? A df of A. Where would it send like a rectangle?
That's a question to the audience.
Yes,
Don't
this
give
is a
them
question to
the
the audience. I'm gonna. Yeah, actually, if you have a linear map, and let's suppose it's invertible, it's an invertible linear map, which means it has a trivial kernel if you want. Like it doesn't send any non-zero vectors to zero. What does the image of a rectangle look like under a linear transformation? Yeah, exactly. So what were you gonna say? Yeah, a parallelogram, it could be resized, it could be sheared, like to be a parallelogram, it could also be rotated in some way. Right, so the image looks kind of maybe like this. I'm very liberal with the space I use for my pictures, but you know, it's more fun that way. F of A is somewhere in there. Under a linear map, it would be something like this, right? But let's see what's actually happening with if this was not a linear map, but the actual function that we claim it approximates. Well, if we have this rectangular domain, right? What does the function do to it? Well, this is a continuously differentiable function, maybe smooth. So it doesn't behave quite as well as a linear map. It could send it to like maybe a curvy kind of rectangle, right? Unclear what it does to it. But if you choose a very small rectangle near A, still, because of this, because we said that the derivative really closely approximates the function near A, and more importantly, the closer we are to A, the better that approximation is. So when we take a very, very small rectangle near A, the approximation of the function by the derivative is even better. So near A, even the image under this function of the rectangle itself is very, very much like a, you know, like a parallelogram of sorts, right? Something like this. And so what this suggests is that as long as the derivative is invertible as a linear map, the error term is small enough eventually if we just pick a very small radius around A. The error term is so small that that would also force the function itself to be invertible near A. Now, I guess question to the audience, just for fun, can we expect to say that if the derivative of A is invertible, then the function is the function is always invertible? Can we say something like that? What do we think? Yes?
Probably not.
Yeah, exactly. What were you thinking? Sorry.
For example, if our map is from a line to a circle in R2, we just points around itself.
Yeah, exactly. We can have a situation where, in fact, it's even possible that the derivative is always invertible, but the function is globally not invertible. So this is really only something we can say about a very small neighborhood around A, that the function on a small neighborhood will be invertible. So let's actually, given this picture, let's state the inverse function theorem. I think, are we okay with this picture? I think I'm just going to erase this and keep that on the board because that feels...
So actually, no, before they continue, let's ask them another question.
Yes.
So what was the claim? The claim was roughly that if f at some point has a derivative that doesn't have a zero, that has a zero kernel, so the derivative is invertible, then kind of around A, the map itself should also be invertible. Now, following question. I have this invertible map. What should the derivative of the inverse of the map be? Okay, but what's the derivative now? It's what kind of object? It's some linear transformation,
yes.
So it should be the what?
The inverse of the
Okay, good.
Exactly.
That's it.
Yeah, and you can think of it as, what does it, like if this little rectangle, or I guess it was a square, got transformed to this parallelogram, the derivative of the inverse should take this little parallelogram near A and transform it back to the square, so it makes sense that, you know, that it would be the inverse of that transformation. Yeah, and that's part of the statement of the implicit function theorem, the inverse function theorem, so let's just state it here. I think I probably should have just erased the top, but whatever.
maybe if you want, maybe you want to write down the statement of the inverse function theorem at the bottom of the board there.
Oh, sure, why
And
not?
then when you do implicit, you'll just have that board for implicit.
Oh, sure, okay. Well, so we'll keep this board for implicit. Let me rotate everyone.
Oh, what? Okay, yeah, this is fine.
Oh, sorry. This computer is using this phone.
No,
it's not.
don't worry about that. This is
It's like
this is the recording.
I can see a little sliver of this. Okay, very good.
Yes.
Nice.
So you want that to be like that, or are you writing on that board?
Yeah,
Okay.
writing on that board. This is actually more visible because there we go. Okay. So let me state the inverse function theorem, kind of what you expect. So if a function f, okay, I don't know how to make this visible. If a function f is from Rn to Rn, and the condition on it is actually enough to be continuously differentiable. I don't know. Do we work with just smooth maps here, or do I say?
It's
say
differentiable at a point.
differentiable. I'm going to say near A, near the point A. Then there exists a neighborhood U. A lot of these functions are stated with a lot of like jargon with sets, but it's like basically just saying the statement that it's locally smoothly invertible. So there exists a neighborhood containing A, and then a neighborhood V containing f of A. These are open sets. Maybe I should specify that these are open.
You can think of them for now as just a ball around a
Yeah.
ball of some
At least you can think
delta
of
radius and epsilon radius.
You can think of this as a ball or a rectangle around A, and this is not necessarily going to be a ball or rectangle because it's just the image of this under the function, which kind of is unknowable. But it's also a neighborhood around f of A, such that the function f, well, it restricts to a function from U to V, has a smooth inverse, or has an continuously differentiable inverse, I guess. Let me just say it has an inverse, yeah. Let me call the inverse G, going from V to U, right?
Just call it f inverse.
Okay. It's easier to write down the derivative when it's called another thing, but let's let's call it f inverse with okay, f A is a point, f of A is a point in the codomain, right? So then we can say now that the derivative, actually I don't need to just say that. Okay, the derivative of f inverse. So the inverse is next to the f.
Put brackets around the f inverse.
Yeah. The derivative of the function f inverse at the point f of p is just, what did we say it was?
The inverse of.
Right, so I have to write the derivative of f at p, right, and then the inverse of that as a linear transformation. Yes? Mm-hmm. Okay, this is the inverse function theorem. I will not prove it, so I will just draw a square here. The reason I will not prove it is because the intuition here is a lot more enlightening than the proof. The proof you can read in Spivak Calculus on Manifolds, kind of like one of the default textbooks for this kind of thing.
Or Moncrief's Calculus on Manifolds.
Yeah, Moncrief's analysis on manifolds is good. Regardless, sorry, that's a terrible square. But the proof is not super enlightening. There's just a lot of like kind of bashing to prove that the derivative is actually given by this, and a kind of clever argument to choose a neighborhood small enough. But it's not particularly enlightening.
Like
so we'll
it's essentially the main thing that we skipped is like the fact that this Rx minus A is somehow is small, and you know those corrections like in some sense don't matter for the invertibility to happen. Like most of the proof is just like bounding errors that come from the Rx minus A contribution.
So like what we did last time.
Well, we didn't do that last time. So we didn't do any of these proofs last time, but yeah, it's just like you bound some error to show that the function is invertible. There is a cute argument that uses Banach contractions, which is essentially the same idea to do with bounding. But anyway, you can read about it. We won't worry about it for now. Okay.
Okay. Yeah, so that's the inverse function theorem, and this is important for the next theorem, the implicit function theorem, which arises very naturally from this discussion, because here we talked specifically about when a function from Rn to Rn and when the derivative was invertible. In other words, as Ivan said, there's nothing in the kernel. There's no non-zero vectors that get sent to 0. Yeah, I will rotate this back to this board now. And now we can ask ourselves a very natural question of, what if the kernel is actually non-trivial? What happens then? So if there are non-zero vectors that get sent to 0, what can we say? And specifically, we can talk about, well, okay, we expect the function in many cases not to be injective or invertible anymore. In fact, for this theorem, for the implicit function theorem, we'll consider the case where we're going from a bigger space to a smaller space, so that something kind of has to be squished to a point, and we'll look at the level set of this function as in the preimage of a point. All the points that get sent to a single point, and we'll see that we can describe that set pretty well using this theorem. But let's kind of think in general what the intuition for this would be. Suppose we have a function from Rn to, like, just for now, let's say just some other space Rk. So f from Rn to some Rk, right? Doesn't really matter what's happening. But suppose, let me take a pretty rectangular domain as always. I like to depict the domain as rectangular to imply that we have some sort of control over it, but the codomain is like some blob. And suppose it gets sent to, like, something. This is just the image of the set. Okay. You know what? Let me be even more pictorial about this and, like, make the rectangle more like a cube in some dimension. And suppose there are. So now suppose we have. Dimension of the kernel of df at a. So that's a lot of things. So I don't know. There's lots of terminologies for this. So I'll just write dimension of the kernel is let's say some number m. So they're near a.
Stop and ask them this as a question.
Yes, will do. So this means that near
what
a.
does this mean?
Okay. Oh,
so
that
like
is a good
dimension
question
of the
also.
kernel dfa equals m. What does this mean in terms of that picture?
Like it's collapsing. Like there's a.
Okay.
Like losing a dimension.
Okay.
That's
sure.
that's
in
not
some
about what you
sense.
think about it. Yeah.
That's right, but I want. That's right. I want to hear this in different words. Suppose you start at A, right? You have a bunch of directions around you. Okay. Some of them are special, and they are which directions?
One's not in the kernel.
There's ones that are in the kernel, ones that aren't in the kernel. Let's look at the directions that are in the kernel. What does that? So suppose you're standing at A, and then you go in the direction of something in the kernel. What does that mean?
Derivative is 0.
Derivative is 0. So as you walk in that direction, what happens?
Yes.
You almost stay still.
Yeah, exactly. And you can even think about if you keep walking in the direction of those, in those directions in which the derivative is 0, you'll actually remain at this point, f of a. Right. Yeah, exactly. So as you walk along these directions, morally, we're kind of like staying at a point. So these are directions along which, if we walk along them, they're
The linear
function is
approximation is
constant.
0. So if you take a really small step, you don't move after being mapped by that.
You move basically by the amount of the error term, maybe.
Yes.
So yeah, this is our intuition, and also, what if? Okay, let's consider a more specific scenario. What if the function is from Rn cross? No, let's say Rm cross Rm. I will change this number so that it's not confusing. No, I will leave this blank for now. And it goes into Rn. All this is saying is it's a function from a bigger space to a smaller space, but I've broken it down into like Rm cross Rn just to see that that it's like this. And now, just to see that there's like m extra dimensions. And suppose the kernel, the dimension of the kernel is exactly m. Actually, I shouldn't have changed it at all to begin with. Suppose that the dimension of the kernel near A is exactly m. Here's another question, just for fun. what is the rank? What are the other? What's like what is the rank of this map? I guess.
N times n.
Sorry.
M times n minus n.
Close. Yes.
M.
Yeah, exactly. It's more like n plus m minus m.
What is Rm cross Rn?
Combined matrix.
No.
Yeah.
No. What is the Cartesian product?
What's the dimension of it?
No. What is a Cartesian product?
It's like one between
Of two
RM
sets.
and one between R.
Yes, that's
Exactly.
right.
So
But
think of R cross
if
R.
I have m numbers in
Yeah.
R and then n numbers in R, that's really what?
M plus n.
Rm plus n.
Yeah, exactly. So we can think of it this way. It's really just saying we're going from a bigger space to a smaller space, but
If it was a matrix, it would say matrices or something.
yeah, yeah. And so the reason I write it this way is because I want to consider as a function of like morally two variables, one of which is a vector in Rm and the other is a vector in Rn.
But you can
This
think
is
of
just-
it as just one
Okay.
m
Yeah.
plus n vector.
This is just
Oh,
one Euclidean space.
okay.
Yeah,
Thank
but
you.
just to be clear. Yeah. Okay, that's a good clarification. Yeah, so as you said, it's basically by the rank nullity theorem that if the rank is and the dimension of the kernel would be m. Okay, that's mostly important when we actually state the implicit function theorem. So I think now that we have this intuition of like, if there's m things in the kernel, there's m directions that we can go to in order to stay constant. That's essentially what we're saying. In other words, so the way I like to phrase it in my head, which is what the implicit function theorem will say, is that means the kernel, in other words, okay, the pre-image of this one point, all the points that get collapsed to this one point, the set, which is the pre-image of this point, is given by like m degrees of freedom. So there's m directions you can go to, and still stay on that level set. So for the implicit function theorem, it's just notationally easier to just call this 0, so to present this as the pre-image of 0. Of course, it could work for any other point. I just don't want to have an f of a in there. But yeah, suppose we're looking at basically the pre-image of 0 under some function from a bigger space to a smaller space. And of course, if you just think of like collapsing R2 into R, for example, it has to be non-injective. There has to be some sort of like the pre-image of 0 has to be, or the pre-image of some points has to be non-trivial. So let's state the theorem actually. This is going to be a lot easier to talk about it if we do. So the implicit function theorem, we'll see also why it's called the implicit function theorem. I haven't really stated that explicitly. I can never spell the word theorem also. There we go, this is probably good enough. The implicit function theorem is if we have this like, again, continuously differentiable function from Rm cross Rn, which remember is just Rm plus n. There's no reason to call this anything. I could have said Rk to Rn where k is bigger than n, but I specifically am interested in decomposing it this way. So I will write it this way. And the reason is because I want to see it as a function of like f of x, y, where x is in Rn, x is in Rm, and y is in Rn. This is for notation. Okay, does this make sense to people? So morally, this is like a function of two variables. And okay, let's look at what the derivative of this looks like. Df at AB. A point in the domain is now AB. Again, A is in Rm, B is in Rn. Yes. What is this? Okay, what is this matrix going to look like? Actually, this is a question for people. What is the derivative of this at some point is a matrix? What are the dimensions of this matrix? Yes.
M plus n times n.
Exactly. So there's m plus n columns and n rows. Exactly. So which is why I'm going to write it kind of this way. Maybe I went too big on the size a little bit. There we go. I want this part to be, this is m cross n, so this part I want to be more like square, right? There's n rows and m plus n columns, and it's convenient to just like, distinguish the m part and the n part. And okay, we were just talking about a scenario where the dimension of the kernel is m. So the assumption for this theorem is actually that this part has non-zero determinant. That this part of the matrix, this is a square matrix, right? Part of this non-square matrix is a square matrix, so I can speak of its determinant. And the assumption is that the determinant is non-zero. So in other words, if I were to actually state the theorem carefully, I would say let M be the matrix of just these partial derivatives, the ones that are on this side. So dm plus j, I think, of fi, for I in 1 through n, right? Yeah, basically the last n variables and all component functions. This the derivative. Yeah, the determinant.
Sorry,
of this
m is the n by n block.
Yeah, and
Maybe
m is the n
label
by n
that
block.
as m in the diagram.
Yes, will do.
Okay. Call that piece m.
This piece, what?
Call that piece m. Okay.
Yeah, this
Yes.
piece is m. M is the n by n block. They just call it m because that's the word matrix starts with m. So.
Oh, I thought it was because minor starts with M.
Oh, yeah. Then if it was minor, I would have used the lowercase m. I got it all planned out. Anyway, yes. So this is the assumption of the theorem, okay? And what this basically just says is, well, this is a function. This is a linear map from Rm plus n to Rn so from an n plus n dimensional space to an n dimensional space. And if the determinant is non-zero, that means, what does that mean about?
It's invertible.
Exactly. So what can you say about the columns of this part?
Linearly independent.
Good, exactly. The columns of this part are linearly independent. And actually, here's another question. What is the maximum, what is the most that the rank can be?
N.
Exactly. It cannot have rank more than n. And we see that it has rank exactly n because n columns are linearly independent. So then what can we say about the kernel?
Size
It's just
n.
0.
Sorry?
Wait, kernel of the entire thing? Or
Yeah, kernel of the entire thing.
is n.
Exactly, because all of these have to,
Linear.
it has to be, the kernel has to be m-dimensional because we've seen that their rank is n-dimensional. So this is, again, a lot of this is just kind of understanding the rank nullity theorem, really. That doesn't mean all of these are sent to 0. It means they're all like linearly dependent with these, right? But point is, this whole matrix has an m-dimensional kernel. This is
In
basically the
principle,
assumption.
if you wanted to, because the input basis and the output basis are different, right? Because I go from a different space to a different space. I could always choose the output basis to be such that those first m columns are just
Yeah.
all 0,
Yeah.
and then the other thing is non-zero.
Like,
But okay, you don't
Yeah.
have to do that.
no, just I want to expand it. Like, it's possible. It's always possible. Like, and I can always organize all the linearly dependent ones first, and then the linearly independent ones like after.
You can do them.
But you can have
Yes,
to
that's a
use
good
it
question,
as
actually. Yes, so it's possible. We'll see an example later where, for example, it could be a function. You know, this is kind of assuming something lucky, which is that all the last columns are linearly independent.
Remember, doing column operations or row
Yes.
operations corresponds to multiplying by an invertible
Mhm.
matrix. Corresponds to some change of basis
Exactly.
Oh,
of
So-
the either output or input.
Yeah, so if we had a function where like some n columns were linearly independent, the theorem would still hold. Theorem which I haven't actually stated yet because we've been dilly-dallying, but that's okay. Anyway, yeah. So the theorem says then. This is a little bit nonlinear storytelling here, but that's okay. Then we can, as I said, what was our intuition before? The intuition before was that if we have m directions in which we can go to and not change where we are, right? M degrees of freedom for the kernel. That means the pre-image of this point, the set of all points that gets mapped to a single point, has m degrees of freedom. In other words, there exists a function. I'll call this y, which is a function of x. So, think again, x is like this Rm piece, and y is this Rn piece, right? What we're saying is there's only m degrees of freedom, so the pre-image of a point only depends on m independent variables. So everything else, this n by n piece, is actually just dependent on those in order to stay in the kernel. Okay, so what this means is they're just a function y of x, which is smooth, such that, oh, I said this before, but I should have written down written this down. Also suppose f of AB equals 0, right? We want to look at the preimage of 0. So suppose the point that we're near is actually a preimage of 0. Okay, good. There's a y of x smooth such that f of x and y of x is 0, right? And of course, like, y of a is going to be b, because this is the point that we're near. Okay, is this, are we kind of clear on why we would expect, why this is the phrasing of this? Why this follows from our intuition? So this is essentially saying that in order to stay on the preimage of 0, so on the set, maybe I should actually kind of draw the set. This is the set that gets mapped to 0. So in order to stay on the set that gets mapped to 0, we have to, there's like only m directions, m degrees of freedom for it, so it only depends on this variable x, because actually both of these inputs depend on the variable x, right? Yes?
You said y is smooth.
Yes.
What did you say about f? Did you
F is, I said continuously differentiable, but F should also, yeah. F is, are you guys okay with the notation C1 to be
Yes.
continuously differentiable? Okay. F is C1. There we go.
And so y is.
Okay.
Sorry.
C1.
You could have gone with smooth.
I could have gone with smooth, but I stated the inverse
Yeah.
function theorem was C1. So whatever. You can replace this with smooth in your head, because that's the only thing anyone cares about anyway, I think. Yeah, okay, so that's the statement of the theorem. Are we okay? Yes. I want to, before I prove the theorem, because the proof is actually really short and sweet, I want to do an example, just so we can see more clearly what's happening. Can I? I'll move this forward.
So I'll just say this again. We've said this many times. What this theorem is saying is, if at every point you have m directions, in which if I go in those directions I don't move. This means that there is a surface, some kind of m-dimensional surface. If I stay on this surface, then after getting mapped by f, I don't move anywhere. Right? That's roughly the idea, right? This y of x is an m-dimensional variable. Y of x is then some m-dimensional surface.
Okay. We'll do an example just so I can quiz you guys.
Sorry,
for
so
like 10
x
minutes
comma y
straight.
of x is overall some m-dimensional surface inside of Rm cross Rn.
Yes, exactly. The fact that it depends on x means it only has m, dependencies, m degrees of freedom that it can vary by. Yes. Okay. Let's do an example. So consider the following function. F of
And
x.
sorry, and the proof of this is actually not bad. You can read this in
Yeah.
Moncrief and probably.
I think I'll prove it pretty quickly today.
Oh, okay,
so.
sure. You'll prove it. Good.
But I want to do an example before we prove it.
Question.
I was just
Yes.
wondering for like the
Oh,
inverse
sorry.
function theorem, do we need it that like it says Rn to Rn? Can it just be any can the output just be any dimension of higher degree?
Well, think about what would happen to the derivative. Would the derivative ever be invertible in that case?
Aren't we picking a subset anyway?
No, you go from smaller to bigger. When you go from bigger to smaller, some stuff doesn't exist.
Yeah.
Oh,
Yeah.
So
it has
imagine.
to be the same dimension.
Yeah. Imagine you're going from R2 to like R3.
Mm-hmm.
The image of a plane, or like the image of a rectangle in the plane in R3 would be like kind of a sheet of paper floating in air. So you don't really have any hope of like inverting this map, because the neighborhood in R3 would kind of be a ball, and that ball would only like intersect this piece of paper on like a slice.
Now,
So there's
this
nothing
is
that will
this is
invert.
actually the non-trivial bit. In some sense, you can think of this as the non-trivial bit of the inverse function theorem. In some sense, you're kind of proving that something two-dimensional and something three-dimensional are like completely distinct from each other. Because I think for inverse function theorem, you prove this as an if and only if statement.
Yeah.
Right? Like if the function has continuous inverse, then it has derivative that's invertible and the opposite.
Yeah.
So if you prove that, then you're essentially saying that like a two-dimensional surface versus a three-dimensional surface are somehow qualitatively different as far as smooth maps. Like smooth
Yes.
maps can tell the difference between an m-dimensional and some other dimensional, surface or whatever. And that's like the non-trivial thing about it.
Yeah. Exactly.
Like a surface is not the same as like 3D
Yeah,
space.
space. Okay, yeah.
That's the non-trivial thing that you're proving in this theorem. That's like the
Okay.
hard part,
Yeah.
in a sense.
Which of course is like different from just like any kind of function. Even continuous functions can be space filling, but of course
Yes.
like just net random set theoretic functions. Of course the cardinality of R and the cardinality of R2 are the same.
Yes, like
So you can totally-
this is the thing. Like in principle, you can have some what's it called? You
Some
can
bijection
have,
of R
You
to
can
R.
have some bijection of R and R2. You can have a space filling curve, I think, as well from R to R2. But now the claim is that if you wanted a smooth map from R to R2 that was invertible, that cannot happen. And so smooth maps, like smooth structure, sees this difference in dimension.
Yeah.
But more on that later.
Yeah.
Just to clarify, smooth means infinitely differentiable.
Yes.
Yes.
Okay.
Even of course we see continuously differentiables enough. We like think of smooth usually.
Continuously differentiable is the derivatives continuous.
Yeah. Like I guess the intuition is if you give your function a notion of speed, then you're saying like you can't go from R to R2 like without going infinitely fast somehow. But yeah, so consider this function from R2 to R.
So you
It's
can't fill R with R2 without going infinitely fast.
yeah, you can fill R2 with R, I guess. But yeah. Okay. This function is going to be very familiar. Is x squared plus y squared minus 1. And here's my first pop quiz for people. What is this set f inverse of 0? Are we okay with this notation of like f inverse of a set? Just the pre-image. So it's like the set of all points that map to 0. What is the set? The set of all the points x, y such that this function is 0. Yes? Yes, exactly. If we can write if
Hold
f of
on.
x, y equals 0.
Hold on. If the person in the back knows the answer, that doesn't mean the people in the front know the answer.
The people in-
No, wait, just continue. I'm like trying to solve it.
Okay, no, you're good. We can write x squared plus y squared minus 1 equals 0, right? That means x squared plus y squared equals 1. This is the equation of a circle.
I think you were
Yes.
good. Like that bogus mistake.
Yeah. Very good. So we have a circle. Yes. So this is this set that is the preimage of 0, and so this is why this theorem is called the implicit function theorem, is because this it talks about defining functions in the domain of f, right? This is all happening in the domain of f. We're defining some variables as a function of the other variables, which is why it's called implicit. It has kind of nothing to do with the image, because the image, as far as we're concerned, is just a point. Or the part of the image that we care about is only a point. Anyway, so what is okay? Oh, another pop quiz. So many pop quizzes. Let's compute the derivative of f at some point x, y. What is this matrix going to be? What are its dimensions and what are its entries?
X, Y, and then X. Or no, wait, Y.
So what is the dimension of the matrix first?
2.
2 by
2 by 1.
exactly.
Yeah,
Right. So it's a 2 by 1. There's an entry here and an entry here. This is the partial derivative in x. This is the partial derivative in y. So what would the entries be? So this is
Just say the answer.
yeah.
Say the answer.
See, now I'm like doubting myself.
Say
No,
the
it's okay.
answer.
2x,
Yeah, good.
And
2x.
the second entry is?
2y.
Okay,
Yeah,
very
good. 2y. So this is a 2 by 1 matrix,
Yeah.
and the implicit function. Sorry.
Okay,
You
no,
have a
okay, yes,
question?
yes.
Right. Remember, the first entry is if I go in the x direction
Mhm.
by a step, how does the function change?
Yeah.
As y is fixed. So that's just ddx.
Yeah.
And then same for the second.
Exactly. And the implicit function theorem says if this part is invertible, what does it mean for a 1 by 1 matrix to be invertible, by the way? Or to have determined
One by
non-zero?
one.
Sorry?
It's non-zero.
Yeah, exactly. So we're saying as long as this entry is non-zero, we can solve for this as a function of this. What does that
Sorry,
mean?
Why
Let's
is
consider
it
a
why is it
point.
important for the second entry to not be non-zero?
Because that's what the theorem says, that the
Okay.
determinant is
So-
non-zero.
Okay,
Right.
good.
Set M was
Yeah.
not true.
Of course, kernel has to be the dimension of the kernel has to be 1 at least. Those are going to be linearly independent somehow because they're just multiples of each other at least. But anyway, let's consider a point where this is non-zero. Where is y non-zero? Probably here. So let's consider the point 0, 1, right? 0, 1? Yeah. The derivative at 0, 1 is 0, 2, right? What are we? We're over here. Remember, this is just this whole thing. R2 is the pre-image of this function, and the circle is it's the domain of this function, and the circle is the part of the domain that gets sent to 0. We remember this, right? Now, when we're near this point, the implicit function theorem. Actually, another pop quiz. What does it tell us about this? What does it tell us about the circle near a point? Yes? Did you? Sorry.
I'm confused.
No.
What's the
What's the
question?
question?
What does the implicit function theorem tell us in this specific case?
You
You have to move not away from the circle.
or
For it to not go to zero.
I would say like you follow the trajectory. I don't know.
What does
Yeah, what does the claim say? We say we can solve, there exists a function y of x, right?
Yeah.
So we can solve for y as a function of x.
You should have them say things more.
Yes.
You're
It's
speaking
just like
to
y
us.
equals plus minus the root of 1 minus x squared.
Yes, exactly. That's the explicit function. That explicit function. Anyway, yes, exactly. So there's a function y of x that such that if y is like y of x together with x are such that we stay on the circle, and we can see this pretty visually, as you said. In this case, y of x is root 1 minus x squared. You said plus or minus. In this case, near this point, it's plus, right? We're on the upper
Oh, I
half of the
see.
semicircle.
Okay.
But even if we didn't solve for this explicitly, we can see that on a small neighborhood, actually the neighborhood can extend to all the way over here, but it doesn't really matter. On this small neighborhood near this point, this is like the graph of a function. This is like the graph of a function y of x, like y is a function of x. Whenever for each x, there's a unique y such that f of x y is 0, right? Does that make sense?
Yeah.
Now, what if we were at a different point? What if we were at this point? At 1, 0. What is the derivative at this point?
2, 0.
Yeah, exactly, 2, 0. So this is not technically part of the implicit function theorem as I stated, because I specifically said it for the case where like the linearly independent part is on the very left. But this same theorem applies here, because this part has determinant non-zero. We can actually say the opposite. We can say that we can solve for x as a function of y near this point.
Is that what you're
Yeah.
saying? So then it's plus minus, right? No matter what.
Yeah, exactly. X of y. This should be
Why?
known
Because
as-
at the top of the circle, being constant meant going
Yeah.
like this.
Yeah.
And on the side, it's going like
Up
this.
and down.
Yeah. So this is, of course, we can see this is not really going to be a smooth function of x as a smooth function of y of x, because like of course there's like it's not single valued, but as a function x of y, for each y there is in fact a unique x, such that we stay on the circle, which is the pre-image of 0. Okay, so this is just an example to demonstrate what this function is really saying. It basically allows you to describe the surface or the set, which is the pre-image of a point, as a nice graph of a function. Okay, are we all good with this?
Yep.
Are we willing and ready to prove the theorem?
Yeah.
Let's prove the theorem. The proof, unbelievably quick actually, but it really helps that we already know the inverse function theorem. So I'll just prove it in this little square. I've really sold how easy the proof is, so now I have to actually prove it easily, which is going to be a challenge. So,
Thank you.
oh,
See ya.
bye, see you. Okay. What time is it actually?
We have
Oh, I'm totally fine on time. Okay, very good. Yeah. Okay. So we have this function from Rm cross Rn into Rn. And we can prove this by helping ourselves with the inverse function theorem, but in order to apply the inverse function theorem, we kind of need a function from the same dimension to the same dimensional space, right? So let's take, so our function is from Rm cross Rn to Rn. Let's define a new function, but just kind of like extending it in a silly way. So proof, let g of x, g of xy. So it's a function from Rm cross Rn. Yes. We want it to be a function into Rm cross Rn, right? So we can apply the inverse function theorem, kind of by magic. That means we basically need to just like add so just cushion with some more components. We can't really do it stupidly by just like throwing in some zeros, because of course that would just, that wouldn't really change anything. That would make the determinant non-zero. But let's define g of xy this way. G of xy is simply, this is m by the way, x, which is m dimensional, then f of x, y, which is n dimensional. Good, so this is a function into Rm cross Rn. Do we agree?
No, I don't agree
You
with
don't?
you, because f, actually, yes, I do agree with you. Sorry,
Okay,
never mind.
yippee. Do we all agree? How I extended this function? So it used to be just a function into this. I threw in another extra Rm in there and just padded it with x. So I just made it map to x and f of xy. So now it's a function into the same space, from the same dimension to the same dimension. Can I theoretically, if I wanted to, could I apply the inverse function theorem now? Or is there something I need? Do I still have it on the board?
Yeah.
Yeah.
Yes, I do. Okay, very good. This is inverse function theorem. I need to verify my important condition, right?
Which was?
What was my
Stop.
condition?
Stop.
I
Let
stated
them
before.
think.
Oh, I'm glad I didn't write it, because now you guys can tell me. What's the condition to apply the inverse function theorem?
Repeat the question.
What is the condition I need to apply the inverse function theorem?
Sure, we straight up didn't write down the statement.
Yeah,
of the
I
inverse
actually,
function theorem.
I wrote down earlier, but not here. So,
So what should be true about the best linear approximation? For the function to be invertible, the best linear approximation should be? Yes.
yeah. So
So-
the determinant of the derivative at the point is non-zero, right?
He
This is just a
forgot
way of
to-
saying it's invertible. I forgot. My bad. But this is good. In the end, that was fortunate, I guess. Maybe we can pretend it's fortunate. So we need to verify that the derivative has a non-zero determinant, that it's invertible, right? Okay. Let's figure out what the derivative of this is. You guys can help me. So dg at xy. It's a matrix. Now we know of what dimension.
M plus n by m plus n.
Exactly. M n n. Let me so it's kind of, I'll decompose it into 4 blocks: an m by m block, n by m, n by n, and then n by m, whatever. That's a lot of whatever. I'll decompose it into these 4 blocks so it's more clear to see what's happening. Okay, what is this map? Let's figure out. Who can help me?
Start with the top left one, maybe. That's the easiest one.
Okay, yeah, top left one. So
How does that block look
yeah.
like?
Yes.
I.
Yeah, exactly. And why?
Because it's just x with respect to x.
Exactly. It's the partial derivatives of this part with respect to this variable. So it's the derivative of the identity map on those. On this part. So it's I
Write some ones.
by n. So
Write some just one.
yeah, that's better. So it's an m by m identity matrix. Yes. Okay. How about let's go to top right.
Erase the dash. It's annoying me.
Okay.
No, not the dash.
Oh.
Do that. Good.
Okay.
Maybe
sorry.
add zeros. Okay, thank you.
Yeah. Can draw a flower if you want.
No, that would be too much.
I'm doing too much. Okay, what about this one? This is the partial derivatives of this with respect to y.
It's zero.
Sorry?
Is it
Does everyone else agree? Yeah. Okay. Good. Exactly. This part is fully just the zero matrix because x has no dependence on y. Okay. What about this bottom part? These are the partial derivatives of f with respect to x and y.
What is that matrix? We already have that
Yeah.
matrix written somewhere else.
It's just the derivative of, like, it's
Yeah.
just that.
Exactly. This is just the block M. So this part, if we hide the part that we like padded it with, this is just the previous.
Yeah, this should be just df now, right?
And
'Cause
this
in the
is
in the
like the
in
whole
the
column
last
is
entries,
df.
it's just f, right?
Yeah, yeah, yeah.
So it just should be d.
Yeah. And this is some whatever. This is some garbage.
Yeah.
Okay. And now let's verify that. Well, we really hope that the determinant of this is non-zero. What is the determinant of this matrix?
You don't compute. I mean, okay, you could compute the determinant, but you don't care about the determinant. You just care if this matrix is invertible or
Also
not.
that, yeah.
Right? And you just look at this matrix, and you know it's invertible, right?
Right.
Because, you know what?
Diagonal
You know that the kind of M entries on the output, those are linearly independent because the top only has one.
Oh, also that, yeah.
Right? And then at the bottom, I know that the star is linearly dependent on the M's. So I can do some kind of row reduction to make the star 0, keep the top M's as something linearly independent, and then this be something linearly independent. And so I know that I can column reduce this matrix to be something linearly independent, 0, 0, linearly independent. And so I know it has full rank.
Yeah, yeah.
Just by, you look at it.
Just by you look at it.
Let's not
Alternatively,
let's not
if you-
compute a determinant.
Okay. I was gonna say if
I
you
don't
really
want to
want,
compute a determinant.
if you really want,
That's a
the
waste
determinant
time.
of a upper triangular or like a block or lower triangular matrix is just the determinant of the diagonal. So it's like the determinant of this times the determinant of that.
Is non-zero.
Determinant of this is 1. Determinant of this is non-zero. So we're
Yes.
good.
Is
If you
that
really,
really that
if
hard?
you really want to not.
It is, but like now you have to prove what he just said.
Yeah,
Well, we
I'm
already
just
proved that
taking
in
L of
240.
240 and
You
247.
proved
for
it in
example.
240, but
Well,
I
yeah,
don't remember how
you're
it
right.
goes, and I'm going to immediately ask you for the proof.
Oh, don't
But
ask.
I don't want
please
to
don't
prove
ask me
anything.
for
I
proof.
want to look at something and just know the answer.
Yeah, yeah. Which you can, yeah. These are linearly independent by assumption. These are linearly independent from anything here because this is all 0. All good. UP. So this is invertible, which means by the inverse function theorem, this map itself is invertible, which you kind of could have known that earlier because whatever is non-injective about this, I also threw in an x, which like keeps track of the first variable. But whatever. The important part is not just that it's invertible; it's also that the inverse is a smooth map, which is what the inverse function theorem gives us. So, by the inverse function theorem, G is invertible, right? Exists G inverse, right? Well, on a small neighborhood, who cares? Smooth, right? And what did we want? We wanted to solve
No, it
for.
has to be C1 because you said C1 in the statement.
How about I just leave? C1. Okay, good. That would be too strong, maybe, to say smooth. Okay, there exists an invert. Okay, so why did we want to invert it? Yes.
Wait, sorry, and G is also C1 because it's a composition. Do you want to write that?
Do you want to write that?
But maybe just say it.
G is C1. Yes.
Because.
Because it is. Look at it. Like,
Okay, as I was thinking, I was about to say
Stop
that
asking
actually.
trivial
Look
things.
at it.
It's a
Look at it.
composition of C1 things.
This is a C1 function. This is a C1 function. If you
No,
have two
you
C1
just have,
functions,
you
it
have a
makes them
derivative
kiss.
and it's clearly continuous.
Okay.
Stop complaining.
Yeah. Also, we took the derivative.
Yeah, we took the derivative. It's
Stop.
fine.
Stop giving me a hard time. Anyway, there is the G has an inverse, right? What did we want? We wanted to stay on the pre-image of 0. So we wanted to look at when the points f of x, the points x, y such that f of x, y equals 0. So consider okay. G of x, y has an inverse. So that means G inverse of what do we want to take the inverse of? So for some point x, and then we want f of x, y to be 0, so let's look at when it's 0. And pop quiz again, what does the inverse of G look like? What is this equal to? It's, okay, nothing specific, right? The inverse function theorem doesn't tell us that much. It's gonna be like something, there's gonna be some y for some y, right? Unique y. But what goes here is my point. Just based on the definition of g of xy.
Not quite.
Not exactly. Don't think about the
Oh,
derivative.
x.
Just think. Yeah. Sorry.
X.
Yeah, exactly. Just x. G restricts the identity in this first component. So the inverse of g looks like the inverse of the g inverse of x0 just looks like xy for some y. So it basically says there's a unique point xy such that g maps it to x0.
Yeah.
Right?
You get the last
Does that make
one.
sense?
Yes. But then the y is unique for each x.
Yeah, y is unique for each x, and moreover, this G inverse map is smooth. So all I have to do is just say, then define, define y of x to be, okay, we need to just take G inverse of x0 and take the second component.
Yeah.
Are you guys okay with this notation as in projection onto the second component, which is just take the second component? Just like start with xy and just take y. It's like the projection onto our end.
Yeah.
Yes? Okay. So just the projection of G inverse of x0, right? What that does is like, again, let's verify for ourselves in our minds that it works. You have some sort of x. You want to find the unique y near AB that's such that f of xy is 0. Well, you want f of xy to be 0, so you want g of xy to be x0, right? So you just take g inverse of x0, and you get some y, for which that is true. That means g of xy is x0, so f of xy is 0, yes? And just steal the y from there, which is what pi2 is doing. Okay, does that make sense? So this completes the proof. And this is, again, since Av would love for us to mention, this is a C1 function, as we said. And this is not just a C1, this is a smooth function, the projection onto the second component. So this in total is a C1 function. Yes?
Decomposed.
Because you compose two C1 functions. Okay, so that completes the proof. And with this example, that's basically all I wanted to talk about, I think.
Yeah. That's good.
Okay. Any
All right.
questions?
Okay. I'll